Alright, in this video we're going to be learning about critical points in Extrema. And before we get started with that, let's review a few things that will help us with this material. So taking derivatives, if I take the derivative of x squared minus 25, I should get 2x. Taking the derivative of x squared minus 6e to the 2x plus 9, I would get 2x. Then minus 12e to the 2x. The 12 coming from the 2 times negative 6. And d dx of 2x squared minus x minus 21 all to the third power will be 3 times 2x squared minus x minus 21 to the second power, and that's going to be multiplied by the derivative of the inside, which is 4x minus 1. And the derivative of ln of 4x would be 1 over 4x times the derivative of the inside, which is 4. So you just get 1 over x. Taking the second derivative means just take the derivative we already had. So the derivative of x squared minus 25 is 2x. The derivative of that would just be 2. And then part B, we would take the derivative of part B from the previous example, and I'd get 2 minus 24e to the 2x this time. We're going to keep multiplying that number in front of e by 2 every time you take the derivative. Solving radical equations, this is going to come up a little bit in this section, so I want to go over it. First, I would subtract 4 on both sides. So, and then we're going to rewrite this. It's going to be minus, well, we'll rewrite it in a minute. Minus 67,375x to the negative 2 equals negative 4. And we can rewrite it and put that x squared in the denominator. So negative 67,375 over x squared. Now, I start over here. Equals negative 4, and then to get you don't want your x to be in the denominator, so we multiply both sides by x squared, and we get, why won't my pen work? Negative 67,375 is equal to minus 4x squared. We can divide both sides by negative 4. And we're going to come up with 16,843.75 equals x squared. And of course, to get what the x values are, I would take the square root of both sides. And there are actually, let's see, there are going to be 2 numbers that make it possible. 129.78 if we round, and negative 129.78. Because if I square either one of those, I'll come up with the 16,843.75. B is going to be similar, so we're going to have negative 30,000 over x squared. I'm going to go ahead and do that right now. Is equal to negative 1.5. So multiply both sides by x squared. So negative 30,000 equals negative 1.5 x squared. Divide by the negative 1.5. And that's a positive 20,000. So taking the square root of 20,000, we're going to get a positive answer of 141.42 and also negative 141.42. Okay, so So the first derivative information, this is something that you've probably already realized, but we're formally mentioning it now, that if the function's increasing on an interval, actually this is review, then for every x value that's smaller than another x value, the y value of those corresponding ones, one will be smaller than the next. That makes sense? And if f is decreasing, then as the x values go down, so do the y values. So we can look at that in a graph on which intervals is this function increasing, decreasing, or constant. Well, I can see that if I start at the beginning and I go up to here, so that's about 0.5. So from 0 to 0.5, we're increasing. So I'm just going to use that up arrow facing up for increasing. And then from 0.5 down to about 2, we're decreasing. And then we're going to increase again from 2 to 3. And then we're going to be constant on the interval from 3 to 4. And you'll notice I'm using parentheses for all of these intervals, so that's because you always use parentheses for talking about increasing, decreasing, and constant. And from 4 to about 6, we're increasing again. And then we decrease from that last interval from 6 to 8. So that's a little review of increasing and decreasing. Now, the part that I said that you might have already realized is when the derivative is positive, then the original function is increasing. If you think of just a regular line, if the line's going up, it's got a positive slope, so the derivative is positive. And if the derivative is negative on an interval, then the function is decreasing. And if the function is 0 on the interval, then the function is constant. So it's not going up or down, the rate of change is constant. So we can use calculus to find if a function is increasing or decreasing. We want to take the derivative, which is 2x plus 5, and we're going to set that equal to 0. Solving for x, we get that x is negative 5 over 2. And this is called a critical point, this negative 5 over 2. It's where the derivative equals 0. Alright, so from there, we're going to put it on the number line. So negative 5 over 2. We need to look at a point before it and after it, so we can get a sense of where this function is increasing or decreasing. So I'm going to test negative 3 and 0. So all I need to do is plug those back into the derivative. So f prime of negative 3 is 2 times negative 3 plus 5. That's going to be negative 1. So we know now that the function is decreasing on this interval. And if I plug 0 into the derivative, so 2 times 0 plus 5 equals 5, the function's increasing on that interval. So we're going to say it's increasing on the interval from negative infinity, no, sorry, that's decreasing. So decreasing on the interval from negative infinity to negative 5 over 2. And it's increasing from negative 5 over 2 to infinity. It's split right in the middle, which is what we would expect because it's a parabola. Parabola is going to be decreasing until we get to the vertex, and then it increases. So the derivative of a function f is a function that gives information about the slope of f. The blank, the derivative, tells us if the original function is increasing or decreasing. Okay, max and min. So here's a whole bunch of information, definitions about maximum minimums. So we have local and we have global. Global means over the entire function, whereas local just means we're talking about a small portion of the function. Well, it might not be small, it might be large, but anyway, it's just one portion, one interval. And in this class, we're mostly going to be dealing with local maximum. We're going to look at max or min just on an interval. So if we look at this picture, it kind of gives you more of an idea of max and min. So minimum is like at the, the low point of a graph, or the low point of an interval. So we have some local minimums here for low points, and then this last point is a global and local. It's global because it's the lowest point over the whole graph. And we have a global max up here because it's the highest point of the whole graph. And we also have a local maximum right there. So we're going to go through with these graphs, and we're going to label max and min, either local max, global max, local min, or global min, or neither. So right here we have a global or a local max. I'm going to call it LMX for short. And right here we have a local min, so LMN for local min. And then another local max. And this point right here is actually a global min, so GLMN for global min. This point right here is neither, but it's called a cusp. Don't worry about that too much, but I just wanted to point that out. And this endpoint, now local min and max can't be on an endpoint because it has to have some points on either side of it, but this is a global max. Now this point here could be a global min, except it's not, because the global min is over here. So this point is nothing. I'll just say neither. In the second graph, my endpoint here is a global max, so GLMX. And we have a global min right here, GLMN. And a cusp, another cusp. Actually, there's two cusps, one right here too. And then we have a global min right here, GLMN, and this last endpoint is nothing, but we do have another local max, so LMX right there. Alright, critical number I've mentioned already. It's when the derivative is either 0 or undefined. And a critical point has both values, the x and the y, so you would just plug the x value that you found into the function to find the y value to find the critical point. So we are going to find the critical numbers of the function f of x equals 2x cubed minus 33x squared plus 108x minus 11. So we need to take the derivative of that, and we get 6x squared minus 66x plus 108. We set that equal to 0 and solve, and I would just use your quadratic formula program since it's a quadratic equation, and you're going to get the points 9 and 2. So for the smaller one we're going to put 2, and the larger one is 9. So this is a little summary of extreme values, maximum and minimum. And then I like the pictures here because it shows you that, right here the derivative is 0, but it's not a max or a min, because on either one side it's going up and one side is going down. To be a min, it would have to be going up on both sides, and to be a max, it'd have to be going down on both sides.